So we're live. Read along with me. It says this. So the goal of this lesson is to represent data using an exponential function and then interpret it. We'll use our graphing calculators to solve stuff. It says the population of Canada from 1871 to 1971 is shown in the table below. In the third column, the values have been rounded to the nearest million, and to save ourselves from typing, we're going to use the third column values first of all, okay? The second thing, it says, using graphing technology, create a graphical model and an algebraic exponential model for the data. How do I know if they hadn't told me that this might be an exponential graph? Get your calculators out, please. There's going to be some questions in the homework where the textbook says, how do you know if this is exponential? The way you can figure out if it's exponential is if you take any y value and divide it by the y value above it, you should get roughly the same decimal answer. I'll show you what I mean. If I take the second y value, 3.23, and divide it by the first y value, I get that. If I take the third y value and I divide it by the second y value, the one above it, close. Not bang on, but close. If I take, this y value, the 10.38, which is the seventh y value, and I divide by the one right above it, the fact that these are all close, if I was doing research, Kayvon, I would start to think maybe it's an exponential graph. So a way you can tell if something is exponential, divide any y value by the one immediately above it, and the ratio, the answer, the decimals, should be close. Maybe bang on, that probably means it's fake data, but close. Hey, let's try the last one, 21.57 divided by 18.24. The first one's a little bit off, but certainly, Brooke, you can see the next three are all pretty close. That would suggest to me this is exponential. Now, the question said in the notes, create an algebraic exponential model. So they said it was exponential, but just because I'm a nerd, I always like to show you trivia. If you didn't know, that's how you could check. Now, what are we going to do? We're going to type this into our stat menu, except I want to cut down on the typing. So instead of going 1871, 1881, I'm going to call this year 0, write a 0 there, because that's the starting population. Start, we never say that's the first population. Start, we say that's at year 0. Those of that are in physics, we would say at time 0. Year 1, year 2, year 3, year 4, year 5, year 6, year 7, year 8, year 9, year 10. So far, so good. And so what I'm going to type in my stat menu is this as my x value, and I'm going to type this column as my y value. I'm just going to get an answer in millions. So I'm going to get out my calculator, menu, stat, clear any tables that you have there. The left-hand column is going to be 0, 1, 2, 3, 4, 5, 7, 8, 9, 10. The right-hand column is going to be really careful when you're typing, 2.44. Anybody not have their graphing calculator here? Now's the time to fess up. Well, I have them here. Oh, I had such high hopes. Oh, you have it here? You don't have it here?
No, I don't.
You have your phone?
Yes.
Bring me your phone, please. So we're back. 2.44, 3.23, common mistake on your test, by the way, Brooke, is going to be typing in the data points incorrectly, so be really, really careful. On a test, it would probably be worth scrolling back through them and checking to make sure you hadn't made any mistakes. Here, we'll use the group method. If we all get the same answer, we know that we haven't made the typo. If someone gets a different answer, they probably made a typo. It says, what does part A say? Uses graphing technology, check, to get a model and get an algebraic exponential model for the data. What would we do now? What have we done with the polynomials? How do we turn this into an first of all, into a graph and then into an equation? What do we hit now? F1 graph. Graph 1 again. Does that look like an exponential curve? Yeah, it kind of does look like one of these. So, okay. That would be another way that I might guess this. But if I didn't have the graph in front of me, the way I might even think about guessing that is by noticing that if I divide any value by the one, any y value by the one in front of it, you get roughly the same ratio. Okay, so let's go calc. Now, it's not linear. I don't want to do that. It's not x squared. I don't want to do that. It's not x cubed. I don't want to do that. Do you see an exponential graph here yet? Hey, let's go arrow side F6. More. Ah, which one do you think I want to try? Exponential, F3. Oh, actually, I want to take that back. Does your menu look the same as mine? Yours has a... Can I see your screen, please? This is where I have a different model. When you hit exponential, okay, yours gives you a b to the x as an option. Now, maybe mine, no, mine doesn't have it there. This could be a problem, Mr. Dueck. I don't want base e. I want, here, let me give that back to you. Give me a second. Didn't try this on my, it would be ironic if this finally... Okay, I think maybe power function? No, it's not a power function. I'm getting a math error. Let me pause the video for a second. This is going to be a problem, Mr. Dueck. So due to technical difficulties, it turns out I don't have the menu that you guys will access, so I can't show you on the screen exactly what we're doing, which means you will have to participate. Once you have entered this, then you choose EXP, exponential, and then what does it say? What are your options? Foster, can you read me each one along the bottom? What are your options? First of all, it says use graphic technology. You guys all got a graph that looked something like that, right? Okay? Which looks like an exponential curve. So, and then we want to choose a, b, to the x. This is the equation we're going to get. So choose that one, which is F2. Is that right? And so what this is saying is your equation is y equals, what's the a value? Sorry? 2.69? 2.67? Okay, no, they should all be the same. What is it? 2.67 of what? What's the base? What's b? 1.24? To the power of x. That's the equation. Except I don't want to use x and y. What's the y variable from my chart? Look at my chart. What are we measuring on the y-axis from this chart? Population. What would be a good variable to use for population? Okay, so here's our actual equation. P equals 2.67 bracket 1.24. What are we measuring on the x-axis? Time. So on my equation, if I enter this data, unfortunately, my equation is going to look different from you because I can only do this using base E. I can only do this using base E. Continue. So I think you still have the 2.66, yes? But I have a different B base. Do me a favor, though, for all of us, though, let's copy it. So go copy and enter to store it in the graph menu. Okay? Guys? Okay? So now let's continue on. We have our equation. B says, assuming the population growth continues at the same rate to 2011, estimate the population in 2011. Now, 2011 would be what year number? If we started out in 1871 with year 0 and we're going up by tens, let's just kind of continue the pattern here. So I would have 1981 would be year 11, right? 1991 would be number 12. 2001 would be number 13. So 2011 would be number what? 14. Is that okay? Is that okay? Not going up by ones, it's going up by tens, right? Okay? Yeah? So let's go on our graphing calculators. Let's go to our menu graph. Select it. Draw. And all of our curves should look the same at least, yeah? Well, let's go to, as I just said, to our graphing calculators, menu, graph, select it, turn the equation on, then hit draw, and we get this lovely exponential graph. Yes? Yes? You're looking, yeah, okay. We want to find out the y value that goes with an x value of 14. Now, there's a problem. I'm going to have to make my graph a bit longer. All of us go View Window, F3. So everybody go View Window, F3. What's the highest x value that appears right now? For me, it's 11.66. What appears on yours? Oh, the same? So I need to get 14. You know what? I'm going to go to a y value of 15. That'll fit it on there. Okay. My y max, I'm not sure if it's high enough. So I'm going to go to the y max, and I'm going to say maybe the population might hit, what do you think the population is in 2011? What's the population of Canada right now? 36 million. So I'm going to give myself some breathing room. I'm going to go 40 million. And now I'm going to hit graph. So exit, draw. There's still my lovely exponential curve. But the whole point of this was I want to find out what y value goes with an x value of 14. And if I didn't move the screen over and up, that value wouldn't appear on the screen and my computer wouldn't be able to, my calculator wouldn't be able to help me. So I had to go further to the right, and then I figured I had to go further up. So now I can go G-solve, arrow sideways. I want to do a y calculation for an x value of, do you guys get approximately 54 million? Yep. Is that right? So even though I have a different equation, my answers will be the same as yours. I'm just in a different base. 54 or 55 million? 54 million. What's our current population? Why, wait a minute, why are we so far off? What's happened over the past 20 years that's different from 1871 in terms of population growth? Family size, family planning. Lucky in 1871, Lucky was the farmer with a large family because they could work for him. I kid you not. They'd done studies at the turn of the century. If you were living on a farm, every child you had earned you about $10,000 of labor by the time they left your house, by the time they grew up. If you were living in a city, every child you had cost you about $60,000. And that's without college. So farmers, to have a kid as a farmer, which our culture back then was mostly agricultural, that was an investment. Now, you guys are money drains. You're horrible investments. We get nothing from you guys. A Christmas card, right? That's it. So families have got, also because kids are less likely to die in childhood. Back then there was a higher mortality rate among children. So what happened in real life is somehow here things started to change. But if our data had been accurate, continuing in our trend, we should be at 54 million. So this is able to tell us something. Around what year, in theory, will the population reach 50 million? Now, 50 million, that's what we put population on the y-axis. So if we go to our graph and we go G-solve, arrow sideways, that's an x calculation when y is 50, right? Around year, well, 13.6. Because 2011 was time 14, 2001 was time 13, and I got time 13.6. Let's try another one. Again, my equation, Caitlin, will look different from yours, but our data in the end will be the same. Turn the page. Sonia did an experiment to determine the cooling curve of water. She placed the same volume. Oh, hang on, let's go back here for a second, by the way. Trivia, look up, look up, look up. What did you guys get for your base? 1.24? Here's what that's telling you. This is telling you the population is increasing by 24%. Where did I get that from? Do you see it? Okay. So if you have a 1 point decimal something, what that's actually telling you, the decimal portion is telling you the percentage increase. And back then, the population starting in 1871 was increasing by 24%. Also back then, we were inviting way more immigrants to Canada. Since 2011, almost every culture, every country has started to change, since 2001, they've started to change their immigration policies because they've gotten stupid and paranoid. The US more than us, but we've bought into some of it too. Turn the page. Sonia did an experiment to determine the cooling curve of water. She placed the same volume of hot water in 3 identical cups, and then she recorded the temperature in each cup as it cooled over time. This graph, as water cools, as time moves forward, does water get hotter or colder? So am I expecting a growth exponential graph, or am I expecting a decay exponential graph? Expecting a decay. Carefully, let's enter this data. I'm going to pause the video. So you're going to have the same number appearing twice. That's okay. Look up. So this is a little strange in that the same x value appears more than once. That's okay. I think our software can handle it just fine. Right? 0 appeared several times. 5 appeared several times. 10. That's okay. Again, we're going to go graph. And I'll choose graph 1. And you can see, yeah, we do have the same data points appearing. That's why you can see multiple dots. But this does kind of look like a decay curve. It does sort of, kind of look like my exponential graph. So I'm going to guess that it is. Now what? I want to find the equation now. Oh, well, actually, A says construct a scatter plot to display the data. I'm going to be clever and just cut and paste mine. Yoink. Got to make it a little smaller, Mr. Dueck. Okay, so there's the data. You can just quickly put some dots and sketch it. That does, to me, tend to look like a decay curve. Might not be, but I think so. So it says determine the equation of the exponential regression function. Again, we used to do these by hand. Thank God we have technology because it used to take hours. Calc, arrow sideways, exponential. Now my equation's going to look different from yours. I think we'll have the same A value, yes? So your A value is 78.68, is that correct? Now, again, your calculator is giving you the equation in that form there. That's what it says on the very, very bottom when you pick that one. Right, Caitlin, you with me okay? So what are we measuring on the y-axis? Look at our chart. What are we measuring on the y-axis? Temperature. What would be a good variable to use for temperature? T. Traditionally, capital T equals. A is 78.68. What do you guys get for your B value? Because this I don't have in front of me. Give it to me to, I'm going to say 4 decimal places. 0.9152? No? 0.9711. Sorry, 97. Good gosh, Dueck. This is why we group source this. 9715 means you got a typo, right? Do we all get 0.9715? To the, what are we measuring on the x-axis? That's why we use a lowercase t for time and an uppercase T for temperature. Otherwise, it's confusing. Okay? Again, if you leave it x and y, Rachel, I'm not going to take marks off, but let's make our life easy. Let's use letters that help us remember what value is where. By the way, here's what's happened. Here's what this is saying. This is saying after every, time in minutes, after every minute, you have 97% of your temperature left. In other words, you lose 3% of the temperature every minute. That's what that's telling you, for what it's worth. So, B says, estimate the temperature of the water 15 minutes after the experiment began. Let's copy our equation into our graph menu. Let's go menu, graph, select it, draw it. Hey, that does look like an exponential decay function. They want the temperature 15 minutes after the experiment began. I don't know if 15 fits on my graph or not, but I'm going to try. So I'm going to go G-solve. 15, is that an x value? 15 minutes, is that an x value or a y value? Look at the table. How do you know? X value, so they want to do a y calculation. 15. Apparently the temperature should be, do you guys get 51 degrees? Celsius or Fahrenheit? What does the question say? Celsius? C says, estimate when the water reached a temperature of 30 degrees. 30 degrees Celsius, did they give me an x value or did they give me a y value? They gave me a y value. They want me to find the x value. So I'm going to again go G-solve, but this time I want to do an x calculation with a y value of 30. Apparently it hits 30 degrees after what? 33.4, well, it says round your answer to the nearest minute. Approximately 33 minutes, about a half an hour, a little more than half an hour. Estimate when the water reached a temperature of 40 degrees. So the theme here, Rachel, is I'm going to give you some data. You can turn it into an exponential regression equation using technology, and then I'm either going to give you an x value and say find the y value, or I'm going to give you a y value and say find the x value. You'll notice, Brooke, I didn't use the table function, and the reason is with exponential curves, it's a lot harder for me to guess where I want to start my value, where I want to finish my value, and what I want my step size to be. It's a little more awkward, so I'm using the graph features instead, the graphing calculator features instead. Try D on your own. Estimate when the water reached a temperature of 40 degrees. I get 23.4 minutes in. So even with multiple data points from 3 different sources, our graphing calculator was able to take that and turn that into a good regression. Oh, one more thing. Can you all go back to your stat menu? Again, go graph, graph 1, calc. Bring up the equation again, the exponential equation. Okay? What's your R value here? Is it close to 1? Not quite. What's in front of it? No, what's right in front of it? Okay, the negative, what that's telling you, first of all, the fact that as a value, as an absolute value, it's close to 1 means it's good data. The negative is telling you it's getting smaller as the x value gets bigger. That's all. But again, I like the fact that my r and r squareds are close to 1 or -1. That tells me this probably is an exponential. In other words, if I tried to force feed this into an x squared, for example, you can see my r squared, not bad. Actually not bad, I'm surprised. If I try force feeding it into a x cubed, oh, I'm surprised, also not bad. This is defeating my argument. Maybe I can force feed it into an x value. There, not quite as good, okay, 0.98. Anyways, the fact that you had values close to 1. The reason, by the way, so many of these work is in real life you'd want 5,000 data points or 10,000 data points. We want to type in that much. But if you're doing research and you have a whole bunch of data, you can get very good r and r squared values, very good what are called correlation coefficients. And then you can be fairly reasonable that your conclusion, very certain that your conclusion is reasonable and accurate. What's your homework? I was hoping to give you a full half hour. I almost gave you that right there.